Okay, so welcome to another lecture of the subject digital signal processing. In this lecture, we will be introducing the concept of fast Fourier transforms. So, discrete time Fourier transform, as we all know, is a method of evaluating Fourier transform of discrete time signals. These Fourier transforms are discrete in frequency. Discrete in frequency. So, the representation of discrete time signals in discrete frequency representation is what is called the discrete Fourier transform, and by definition the Tweedle factor Wn is defined as e raised to the power minus j 2 pi by n. So, like all other transforms, the complex exponential is raised by a negative power, but in this case in the literature it has gone like this. So, Wn is positive, but in definition it is negative. So, it is still complex exponential raised to the power e raised to the power minus j 2 pi by n. The summation is in variable n, and for each k we identify the integrals. Therefore, the k is between 0 to n minus 1. In total there are n points for k as well. Now, if this is the case, for evaluating this discrete Fourier transform, multiplications for each x of k requires n complete multiplications, and since the value of k is from 0 to n minus 1 also, so therefore we require n into n, that is n square complex multiplications. Similarly, you can understand that if the summation goes from 0 to n minus 1, there are total n entities which need to be added. So, in total n minus 1 adders are required, but n minus 1 multiplied by n will be the total number of complex additions. So, this much of computation is required while evaluating discrete Fourier transforms. The discrete Fourier transforms are only useful if there is a computationally efficient method of obtaining this x of k in computer systems, because it has to be processed digitally. For that purpose, fast Fourier transforms are used, and fast Fourier transforms are not any transforms, they are a method to evaluate discrete Fourier transform capital X of k for any discrete time system signal x of n, but using a computationally effective method. For that, just a brief about it, will not go in details, but the x of k can be written and divided into xn for n values where n is even, and Tweedle factor raised to the power kn plus remaining x of n's which are odd numbers, odd integers, n is odd, Wn raised to the power kn. So, that can be broken down, and the symmetricity property of Fourier transforms of the Tweedle factor can be used. So, which means to say, if I break the previous summation into even and odd components, it is possible to actually find and divide. So, this will be n by 2 points and these will be n by 2 points. So, we can compute n by 2 DFT and n by 2 DFT, and these can be used to obtain x of k. So, this x of k will be for from 0 to n minus 1, n by 2 minus 1. But since it is still a DFT, so periodicity property exists for DFT. For DFT, the periodicity of Tweedle factors is Wn raised to the power k plus n shall give me Wn raised to the power k by. And the proof is very evident from complex exponential properties. So we basically obtain x of k using two n by 2 DFTs. So it is now each one of them is periodic with n by 2. So now using the symmetric property of trivial factors, we can compute the DFT of remaining, very important, remaining n by 2 points using the already stored value of f1 of k and f2 of k. So therefore, it is possible in principle using the symmetric property of trivial factor. This is periodic static property and symmetric property of trivial factor, that computation of these n by 2 and n by give me x of k for half values, and for remaining half values n by 2 plus 1 till n minus 1 can be computed using the same value. So the computation algorithm mathematically approximately becomes half. This can further be extended because this n by 2 point can be written in terms of two n by 4 points, and the remaining n by 2 n by 4 can be, so these this is from again 0 to n by 4 minus 1. So these points can be evaluated from here, and remaining n by 4 points can be computed using the periodicity property that this is n by 4 DFT. So if I add n by 4 here, this is kn plus n by 4 is equal to k, and because it is periodic. Similarly, this v1 of t, v1 of 2 will also become equal to k for k is equal to n k plus n by 4. What changes is the sign. So what we are using, we are again breaking down f1 of k into 2, and similarly f2 can be broken into v21 of n by 4 and v22 of n by 4, and v21 of n by 4 minus trivial factor n by 2 raised to the power k v22, which we will see later on. This can be easily modified into this for purposes, because we are calculating endpoint DFT. So we will like to use and store only one trivial factors value. So what is important is that it is possible to only calculate half number of DFTs and use the remaining half for computation by using the trivial factor and its negative signs. So the computational complexity mathematically is possible to make it half, and this is what is known as fast Fourier transform for evaluating discrete Fourier transforms, and this is called decimations. So So the first kind of decimation that we will study is decimation in time. In the previous slide, we discussed that it is possible to take half DFT at once and other half, and use the half calculation to obtain the complete calculation. So how many calculations that we can do is actually given by n is equal to r raised to the power v, where r is called the radix of the DFT. Generally of interest is r is equal to 2, so it is called radix 2 fast Fourier transforms. In radix 2 fast Fourier transform, we basically have the number of points for which DFT is calculated related to 2 raised to the power v, where v is the number of stages. So suppose we are talking exclusively for the case of n is equal to 8. We are calculating for n is equal to 8. So for n is equal to 8, if we are evaluating, we can understand that the indices of time is from 0 to 7. So if we take, just for understanding purposes, if we take the even portions alone, so it becomes 0, 2, 4, 6, and the odd components 1, 3, 5, 7, and a second shuffle, because how many stages we will have for this? This is equal to 2 raised to the power 3. So in the second stage, we again calculate n by 4. So if we calculate n by 4, it becomes 0, 4 will come together, and 2 and 6 come together. Similarly, here 1 and 5 come together, and 3 and 7 come together. So that the indices in which manner we will compute the decimation in time, DIT, FFT, is also sometimes discussed in terms of the bit reversal that will take place. So suppose the for n is equal to 8, the numbers are 0 to 7, so they are represented in digital 000 to 111. If we perform simple bit reversal here, so suppose I write this, I write 100 here, the bit reversal does not changes for this. This is 110, this is 001, and this is 101, does not change, and this is 011, and this is 111. See, if I write the index for reversal, it becomes 0, it becomes 4, it becomes 2, it becomes 6, it becomes 1, it becomes 5, it becomes 3, and it becomes 7. The same concept that I was discussing, that this actually leads to this, and this conceptually leads to this. So we basically have indices of even orders and odd orders arranged together in this fashion. So we will have 0, 4, 2, 6, these are the sequences, and 1, 5, 3, 7 for odd, and then we can compute the DFT using the butterfly diagram. That the construction is something like that. First of all, since it is decimation in time, the xn, the time indices are 0, 4, 2, 6. So if it is 0, 4, 2, 6, we'll just shuffle the values. We'll see in an example also, shuffle the values of x. Then the computation is that one stage will be like this. The first stage. The first stage is for n is n by 8 basically. So n by 8 means it will be for 2. So one components each. So the signal flow will be like this. So computation takes place like this, and in the computation, in all the lines, the second line will be all minus ones, and the twiddle factors will be Wn raised to the power 0. Then we will have a of 0, suppose for our understanding, a of 1, a of 2, and something like this. Then we again move forward to the next stage. Remember, for n is equal to 8, we will have 3 stages. Now we will take 4 components at a time. 4 components means the first will be connected to third, the second will be connected to fourth. So this will be like this. Similarly, in the letter 4, the indices 4 will be connected to indices 6, and similarly 5 will be connected to 7. The reverse order will also be applicable. Then these lines will be made negative as per computation using the twiddle factors symmetries property, that in this case it will be Wn raised to the power 2, Wn raised to the power 0, minus 1, again Wn raised to the power 0, and Wn raised to the power 2. In the last stage, we will take n by 2. So n is 8. So we will have 4 and 4. So connection will be between first 4 and last 4. So in the next stage, we will have 4 and 4. This b of 0, suppose this is b of 1. So in this case, if we have these b0, so b0 will be connected to b4. Similarly, b1 will be connected to b5, b2 will be connected to b6, and b3 will be connected to b7. And reciprocal connections will also be there. That means b4 will be connected to b0, 5 will be connected to 1, 6 will be connected to b2, b7 will be connected to b3, and the last 4 will be negative, and total factors will be Wn raised to the power 0, 1, 2, 3. The negative signs will be here. If we compute this, because it is decimation in time, decimation means reversal, bit reversals are in time domain, we will get capital X at the last stage, and those capital X's are in its order, which means capital X of 0, capital X of 1, 2, 3, 4, 5, 6 and 7. So in this manner we can compute the fast Fourier transform for n is equal to 8. The butterfly diagram it is called. It can be extended to n, which is of order 2 raised to the power v. Now the Twiddle factors that will be required in this case will be, you can understand, e raised to the power minus j 2 pi by 8 into n, which means w8 raised to the power 0 becomes 1 and w8 raised to the power 1 becomes, from this expression it becomes e raised to the power minus j 2 pi by 8, which becomes e raised to the power minus j pi by 4, which is cos of pi by 4 minus j of sine pi by 4, which is 1 by root 2 and minus j 1 by root 2. Then we will have w8 raised to the power 2, it will become e raised to the power minus j pi, which means it is minus j, simply it will be cos pi, it will be, yeah, and then we will have w8 raised to the power 3. So this will be just complex not complex conjugate of it, you can take it, it will be minus 1 by root 2 and minus j 1 by root 2. So using these 4 values we can always evaluate the butterfly diagram. The butterfly diagram in this case is like this, the simplest butterfly diagram. So suppose here we have A and here we have B, then as for connection, since negative sign is here, we will here always get A plus WNC into B, and here we will get A minus WNC into B. Correct. So this will be how we solve the DIT butterfly. The butterfly for another case is different. Suppose I have just for example, just how the bit reversal is done. We have an xn which is 8.1 by 2, 1 by 2, 1 by 2, 1 by 2, 0, 0, 0, 0. So what is the values of n? This is 0, 1, 2, 3, 4, 5, 6 and 7. So what we do? We take 1, we take 4, we take 2, we take 6. So which means it will be 1 by 2, 0, because it will be 4, 4 is 0, 2 is 1 by 2 and 6 is 0. So it is 1 by 2, 0, 1 by 2, 0. The next is that we take odd components. So 1, 5, 3 and 7. So 1 is 2, 1 by 2, 5 is 0, 3 is 1 by 2 and this is 0. Suppose I go to the this matrix, the values that I will get for solving this, just for an illustration purpose, this slide is the butterfly diagram. Now you can create with your understanding. The points will become half, 0, half, 0, half, 0, half and 0. So first step is this, and then we evaluate, like at this point it will become half plus 0. You can understand, half plus 0. Here it will be on the other hand half minus Twiddle factor into 0. First of all it is 0, it does not make any sense, and w8 raised to the power 0 is also 1, so that does not change, and in all cases it will be like this. So you can understand at odd points will be half. In this manner we can go on and compute the complete stages if we are comfortable with it. So this will be x of 0 into wn 0 x4, this will be x of 0 minus wn raised to the power 0 x of 4. So in this manner we can evaluate. If we go to the later stage, if this is suppose a naught, a of 0, then it will be a of 0 and plus from this point wn 0 a of 2, this will be a of 2. Similarly the next one will be a of 0 minus wn 2, because now the total factor at this location is wn raised to the power 2. So we will have this calculation. If these are b zeros and this is b1 suppose, and we go down like this, then the x of 0 can be computed by this line, which will be b0 and from this. So this is b of 4. So Twiddle factor is wn0, so multiplication of Twiddle factor and then b of 0. This is b of 4. Similarly, if we go below it, it will be b of 1 plus wn raised to the power 1 b5. Wn raised to the power 1 means w Wn raised to the power W8 raised to the power 1 basically. Okay. So in this manner we can calculate all the remaining points, you can see, and we can go on and obtain the values of x of 0. So suppose for an illustration purpose, I take x of this is the construction for obtaining the DFT that we have seen. Now we take an example, and the examples that we'll take will always work on this property, symmetric property of DFT. So if xn makes a discrete Fourier transform pair with capital X of k, then x of k is x complex conjugate n minus k, where so it is basically symmetric in complex, which means real will be xr. If it is the real component, that real component will be capital X r of k will be capital X r n minus k, and imaginary will be minus times of capital X I of n minus k. So basically this property is sometimes very helpful. We will see after computation of DFT that few points are complex conjugate. So that comes from this property. So suppose we take a DIT example, xn is 0, 1, 2, 3, 4, 5, 6, 7. Now if I go on and make out the first stage looks like this, and the values that I have taken from the numerical itself is basically, you can understand, so 0 is 0 and 1 is 1. So basically all these points are very straightforward. This is 0, this is 4, this is 2, this is 6, this is 1, this is 5, this is 3. The values are equal to the indices basically. So if I compute at this point, you can understand it was 0 plus 4. Here it will be 0 minus 4. It will be 0 minus 4. Similarly, at this stage, it will be x of 2 from the lines plus x of 6. But the indices are the numbers. So it becomes 2 plus 6. It gives me 8. And similarly, we get a minus 4 here. We can go on and compute the first stage, and the values are like this. In the next stage, if we compute, the connections are like this. The first goes to the third, second goes to the fourth, and vice versa. Similarly, for the next stage, the decimation is like this. The total factor values are Wn raised to the power 0 and 2. So if I now calculate at this stage, you can understand this will be multiplication, this will be actually 4 plus W8 raised to the power 0 and multiplied by 8, because this is 8, isn't it? So we get a, if these are my a of 0, so this will be b of 0, and b of 0 comes out to be 12. We can go on and clarify that all other values are the ones that I have already evaluated and posted in the slide. So it is for the viewers to compute and verify that whether these values are arriving or not. You go to the last stage. So 4 and 4 connections are there. So first goes to fifth. The connection is first to fifth and second to sixth. Similarly, vice versa is there. So if in this fraction I compute, minus 1s are in the last 4 stages, and total factors are Wn raised to the power 0, Wn raised to the power 1, 2 and 3. So if I evaluate, capital X of 0 is 28, capital X of 1 comes out to be minus 4 plus j 9.656, x2, x3, x4, x5, all the values I have computed, and it is for you to evaluate and confirm that whether this is what is coming or not. This is the example of DIT. Now there is also concept of DIF. So in DIF, the connection is made such that the twiddle factor comes later on basically. So if I have A and B here, this will be decimation in frequency. Decimation in frequency. In decimation in frequency, the connections are such that the decimation takes place later on. So capital X will be off order. So we basically will have x of n to the left and capital X of k on the right. This will be in 0, 4, 2, 6 and 1, 5, 3, 7. This will be 0, 1, 2, 3, 4, 5, 6 and 7. This will be the first of all the decimation, because decimation will be in frequency. The final stage will come the first stage, the second stage remains the same, the first stage becomes the third stage. And in calculation, if you can see here, it is a plus b, because the b is not getting multiplied by anything. At this point it will be a minus wn cb. So it is very important in butterfly of this decimation in frequency, it is a minus wn cb. So if I have suppose x of n 1, 2, 3, 4, 5, 6, 7, 8. So indices are 1 more than. You can understand the indices are n is equal to 0, 1, 2, 3, 4, 5, 6 and 7. So these are my indices. It is basically 1 ahead of it. So if it is so, the diagram will be such that I have x of zeros here. These are a small x of n's. So these are time signals in the same order. Decimation will be in frequency. We'll first of all have that 4 and 4 stages. So one will be connected to 4, one will be connected to 5, and 2 will be connected to 6, and similarly 3 will be connected to 3 plus 4 7, and 4 will be connected to 8, and opposite lines will also be there. In this case also minus will be in the last 4 stages. Just the twiddle factor placement is here. The twiddle factors are after the lines. The DIF butterfly is such that the twiddle factor gets multiplied after. Similarly, in the next stage we will have 4 and 4 combinations. The above 4 will combine themselves. The first will be connected to third and second will be connected to fourth. Similarly, a vice versa connection will be there. Apart from that, in the last 4 it will be again the fifth will be going to 7th and second will be going to 8th, and vice versa connections. The last 2 will be negative signs in both the butterflies, and twiddle factors wn0 and wn2 will arrive in the last 2 of each pairs. And finally, I will have a single DIF butterfly, but twiddle factors will be last. However, they do not make any difference since they are wn raised to the power 0. If it is so, what will be the computation? The computations will be, in this case, like it is x of, how will I compute? This is x of 4 lines. So at this point I have x of 0 plus x of 4. So x of 0 is 1, x of 4 is 5, and there is no twiddle factor. So I get a of 0 as 6. Similarly, at this point it will be 2 plus, you can see this line is coming from here, it becomes 6. So it will be 8. It will become 10, it will become 12, because there is no participation of twiddle factors in the above 4 lines, because in DIF the signal is coming without multiplication of twiddle factor. The twiddle factors are at the later stage. In the remaining 4, you can understand the calculations will become the same. It will be x of 0 minus, now twiddle factor raised to the power 0 multiplied by x of 4. So it will be basically 0 minus 5, which is minus 4, and then the twiddle factors will come into picture, because here the twiddle factor is wn 1, 2 and 3. So we will have these values, you can verify them. Then we go to the next stage. So in the next stage, if it is a of 0, this is a of 1, so you can understand, and this is a of 3 and this is a of 4, then you can quite easily note that this will be a of 0 plus a of 3. Similarly, this line will be a of 1 plus a of 4, because the twiddle factors are not getting multiplied at these 2 points. So these 2 points will be straightforwardly multiplied with the above one. So what the values we are getting? We are getting 16, which is basically 6 plus 10, and 20, which is basically 8 plus 12, isn't it? We can verify for other complex values also that the values of b naughts are like this. And now if these are the values, understand that this is b of 0, this is b of 1, this is b of 2, b of 3. I will just illustrate one. So here, since the twiddle factor is there, but it does not hardly make any difference, because it is raised to the power 0 in all the cases. So therefore it is basically 1, but still we should consider it. So this will be b of 0 plus b of 1 and this will be b of 0 minus w8 raised to the power 0 into b of 1. So the values that we are getting is 36 minus 4 plus 4j minus 4 minus j4 minus 4 minus j 9.656 minus 4 minus j 1.656 plus minus 4 plus 1.646 and minus 5 minus 4 minus j 9.656. Now the most important thing is that decimation has taken place in frequency domain. The decimation has taken place in frequency domain, which means that the indices that we are getting is 0, 4, 2, 6. So this will be 6. And then we are getting 1, 5, 3 and 7. So the DIF that we are getting is 0, 4, 2, 6. The order of k that we are getting is this, and 1, 5, 3 and 7. So you can understand the decimation has automatically taken place in the frequency domain, which is a very important aspect. The main difference between using the butterfly diagram also we can use for calculating the inverse Fourier transforms. The calculation for inverse Fourier transform can be defined using this formula, where x of n is basically 1 by n, and summation will be actually not in n, it will be in k, sorry. So k from 0 to n minus 1, and we will change the values of n. We will change the values of n from 0 to n minus 1, and there is of course a factor of 1 by n. This is the, so if I plot the butterfly diagram for this, the structure will be similar to DIF. The twiddle factors will now be of negative sign. The structure will be of DIF, which means the 4 and 4 stages will be here, then 2 and 2 stages will be there, and then 1 stages will be in the last stage. 3 stages will be there for n is equal to 8, of course, and the twiddle factors will be multiplied after the signaling points, because it is a DIF structure. It will be DIT actually. It will be calculated using DIT, but since we are actually evaluating inverse, so everything gets reciprocated, and the calculation will be such that in the first will of course in the FFT plot will on the left hand side have x of k, and we'll get x of n. The x of k will be from 0 to n minus 1, and these will be decimated. These will be decimated. Similar to DIF everything, but just that a capital X will be on this side and a small x will be on this side. So the butterfly diagram that we will have is something like this. We'll first of all have capital X values. These are the Fourier transforms that we have taken. Understand this is decimation in time. The decimation, that is shuffling of bits, will be observed on the right hand side. So capital X is applied here, and the connections of 4 and 4 is here. The connection of 4 and 4 is here. The connection is from the 1st to 5th and 2nd to 6th. Similarly, it is from 3rd to 7th and 4th to 8th. The inverse also exists. The negative signs will be on the last 4 stages. Twiddle factors will be after and of negative signs. So negative sign means it will be W8 raised to the power 0, W8 raised to the power minus 1, minus 2 and minus 3. Similarly, we will have 4 and 4. So 4 and 4 means first will be connected to 3rd, second will be connected to 4th. Similarly, the inverse structure will be there, and the 5th will be connected to 7th, and 6th will be connected to 8th line. The reverse also exists. Negative signs will be on the last 2 of both, and twiddle factors will be after and of negative powers, correct. So now the last stage will be the single structures, and W8 raised to the power minus 1 will minus 0 will be there. Finally, we get small x's. So this was frequency. This was frequency. This is time. So what is time? X of n. But x of n may n is decimated. N is decimated. So you can understand we'll get x of 0 to x of 7, but before that also there is a factor of 1 by n, because in the definition it has to be in the definition of inverse there is 1 by n. So 1 by n multiplied by x of 0, we will get x of 4, x of 2, x of 6, 1, 5, 3, 7. So in this manner we can obtain inverse Fourier transform using fast Fourier transforms. So in fast Fourier transforms, we have this decimation in time and decimation in frequency based on from which side the decimation has taken place. If decimation is in time, the indices of time get reversed and vice versa for frequency. So in this manner, we can efficiently compute discrete Fourier transforms using fast Fourier transforms. Thank you.